Thank you.
Okay, Nathaniel, I think we're about at 11:20, looks like, or
Wonderful.
Eastern.
Mm-hmm.
So should I go ahead?
Go, take it away.
All right. So thank you very much to Nathaniel for running an excellent session number 1, and I will be the chair for session number 2. As a reminder, the full agenda is available. The link is in the chat there if you've lost it, so you can follow along. And this session is concentrating on the, you heard about the personal space weather station a little earlier. This is concentrating in the engineering and science that we hope to be able to do, at least some ideas. And so I'd like to invite the first presentation, which is by Jules Madey and colleagues. And that's titled, it's about the ground magnetometer hardware that will be part of the personal space weather station. So, Jules, are you here?
Yes, I am. I believe the way we set this up, Dave Witten was going to give the first part, and I was going to follow with the second part.
I see.
And then let's see, Dave, are you here?
Dave is
Yes, I am.
Great.
Okay. Do you want to start then?
Yeah, let me just share. I've just got a few slides, and I'll do it quickly.
Excellent. Take it away.
Let me get that right.
While you're doing that, just as a reminder to the people in this session, we'll give you kind of a 2-minute warning when we're near the boundary. And so there's that. Anyways, go ahead.
Well, I shared the wrong screen, but it's the same stuff. I was just going to make a couple quick comments on the our efforts to characterize the space weather station, the magnetometer aspect of the space weather station equipment. This has involved myself, Hyomin Kim, who will give a more scientific presentation shortly. Julius has done the yeoman's work of putting some rigor in all this, and Dave Larson has been very helpful. It's been an ongoing effort. There were some initial rough goals that were established to about what might be useful to use as a magnetometer sensor to complement the RF sensors in this project. And the goal was to use something inexpensive enough that we could establish a densely spaced magnetic field sensor network, and that we could measure the field variations in 3 components. The target performance level was roughly 10 nanoteslas field resolution at 1 second per sample. But that's definitely a target based on what's possible. We'd love to do better. And I think we've pretty much got to this level, is my understanding, but we'd like to have the option of doing more. Time varying field measurements are sufficient. Absolute measurement, of field strength is not a goal. There were early prototypes built of all sorts and varieties to try to build something stable enough to test with. We've ended up putting them in the ground, and they've occasionally suffer various insults from groundwater and other things. We've been working on ways to eliminate that. Current work involves more software development. The low-level software keeps evolving. Hopefully that'll inform the final network design. There's both low-level and user-facing software, and support for alternative strategies such as arrays of magnetometers if those turn out to be desired at some point. We don't know yet, but there seemed to be some interest. We're currently working on a user-facing configuration and installation tool to help to assist in appropriately setting up the devices. Some mechanism for real-time monitoring would be nice, though it's secondary. It would be very nice to have a utility for this. And
David, this is Phil. Your slides are not moving. Is that intentional?
They're not. Oh,
You're still on slide 1.
Oh, I'm looking at the wrong screen. Okay. So I'm very sorry. Let me just do it this way then. I've essentially been going down these. There was a prototype markup. I was going over the current work, software development, software utilities, format. I was about to mention that there are some, want to have some format translation tools to assist in comparison with calibrated sensors of established quality. We want to evaluate more precise options for specialized experiments, perhaps some flux gate magnetometers rather than the impedance. I'm sorry. The inexpensive magnetometers we're currently using. Any other options that come along? It's looking like there's a variety of approaches out there. Sighting and packaging, optimal packaging for sites in temperate environments and also for extreme environments. And some rough references to some components we've used in this process. That's pretty much my thing. I'm sorry about the looking at the wrong monitor. I don't know where this one came from. That's pretty much it from me. So I will unshare that and give it back to you. And go on to Jules.
So yes, Jules, you are going to share your slides, I assume, or
Yes.
Okay,
Yeah, I
great.
did. Let me go into share mode here. Now what I'm going to be doing, oops, that's not the screen I want to share. Here we go. That should do it. Okay.
Okay, we can see the Phantom PDF.
Now let me see, let me go to full size mode here. And then let's go to this. Oops, nope, hang on a minute.
Sure.
Right, what I want to do is here. There we are, okay.
Got it.
I'm not going to be doing a conventional set of presentation slides, but these are a series of PDFs. The RM3100 magnetometer, which is a 3-axis magnetometer developed by P&I Corporation that Dave mentioned. We'll show a photo of that. Dave originally developed a support board for it that was able to be used with the Raspberry Pi. And the communications mode with the RM3100 was I2C. Now, the interesting thing about the I2C bus is that it can be extended using a differential driver over Cat5 cable out to over 400 feet. But initially, it was hoped to at least go to 100 feet. The SPI bus, which is the other interface for the IC or for the RM3100, is not as extensible. And even though the I2C bus by itself is fairly short, the differential extender chip, the 9615, enabled us to really consider remote location, which is necessary for a magnetometer. Sensitivities that we're looking at, because local activity can significantly change the or affect the readings. For example, a magnetometer which I have installed roughly 100 feet from the house is, and I'll talk about the subsurface mounting in a bit, underground. If you go by that within rather 2 to 3 meters with a metal wheelbarrow, steel wheelbarrow, you will get a change in magnetic field, a spike of at least 100 to 200 nanoteslas. Now, to give you an idea of what we're looking at, the Earth's field, the maximum Earth's field, is on the order of 50,000 to 60,000 nanoteslas. However, we're looking at variations that are on the order of, hopefully, 5 nanoteslas or even less if possible. Dave mentioned 10. We've easily made that goal and are really at the 5 level and possibly even at the 2.5 nanotesla level with the current magnetometer. At any rate, these are fairly small changes. We look at 3 axes, the z-axis, the vertical axis, an x-axis, which in conventional magnetometry alignment is aligned with the magnetic North Pole, and then the y-axis, which is at right angles to that. Now, the y-axis typically is a fairly small value because in steady state conditions, we want to align that so it's 0 or near 0. And we're looking at small changes that are relative to the shift in the x-axis and the z-axis. And that is reflected in the y-axis, and Heilman will talk to you more about that later. At any rate, getting back to the extension of the magnetometer, it wasn't clear how well that would work past 100 feet. In fact, whether it would even work at 100 feet. One of the slides you see here is a depiction of the current and voltage draw at the end, at the 100-foot end of the test cable. This is using the differential extender again. Power supply voltage supplied it on the Cat5 cable by one pair is 5 volts. Ground is the other pair. The other 2 pairs are used for the differential SDA and SLC clock signal, data and clock signals. Now, the yellow trace that you see in the upper panel is the current draw at the far end. The blue trace is the change in voltage due to that current draw during a clock burst. The upper trace, the purple trace, the violet trace is the I2C clock signal during that data transaction. At the far end, at the remote end, the 5-volt power supply is bypassed with a 220 microfarad capacitor,